Hello friends, welcome to a quiet voyage across Earth's long memory, a story written not in words, but in ice, stone, and breath. Tonight, we drift through 7 great climates, from the molten haze of our beginning to the frozen hush when even oceans slept. Each age left traces, gases caught in bubbles, warmth held in shells, the rhythm of survival itself. So, settle in. Let the story move slowly, like continents shifting under calm seas. And if this journey through time soothes your thoughts or stirs your wonder, like, share, and subscribe. Help us carry Earth's long story to others who love its quiet resilience. The world you stand on was never guaranteed to survive itself. It froze solid, burned alive, drowned in its own air, and still began again. To understand our calm, you have to see the chaos that built it. Earth formed about 4 billion years ago from dust, gas, and collisions that stitched a sphere of rock and metal. Early heat came from impacts and radioactive decay, driving oceans of magma and a heavy steam atmosphere. In time, water condensed, seas gathered, and crust thickened into rafts that would later drift. Through it all, climate shifted in grand chapters. Hothouse intervals with warm polar coasts, and icehouse spans with great sheets advancing across continents. Greenhouse gases steered much of the change. Carbon dioxide, methane, and water vapor absorbed outgoing infrared energy and set the thermal baseline. When their amounts fell, the surface cooled. When they rose, warmth held fast. Cycles in Earth's orbit, eccentricity, tilt, and wobble tuned sunlight by small degrees, but oceans and carbon stores amplified the song. Life interacted with this machinery from the start. Microbial mats trapped carbon. Forests later built coal. Shells locked carbonates in stone. Oxygen rose in steps, allowing complex bodies to breathe and altering gases that sculpted temperature. Over hundreds of millions of years, continents assembled and broke apart, redirecting currents and winds. Ice waxed and waned. Seas rose and fell. Through each turn, the planet remained lawful, not volatile. A system balanced by feedbacks that resist extremes, then yield when thresholds are crossed. The 7 climate ages in this journey are not a list but a rhythm. Fire and steam, methane-blue seas, oxygen's chill, global ice, a recovered greenhouse, a deep-time seesaw between cool and warm, and the recent pulse of glacial cycles framing an interglacial calm. Facts will come gently, placed where they can be held. Rest with them as they pass, like lights along a slow road. If your eyes grow heavy, let them. The planet's long memory can carry you. The narrative will keep its pace without you. The newborn Earth glows, not as a planet yet, but as a wound of stone and fire. 4.5 billion years ago, every horizon was molten. Meteoric impacts fell like rain, each one releasing heat enough to melt the crust anew. The air, if it could be called air, was a dense shroud of vapor and carbon dioxide, sulfur, and metal ash. It pressed down like the weight of a sea. In that suffocating sky, lightning tangled with steam, and volcanoes breathed out the gases that would one day make oceans. The heat came from within as much as from above. Short-lived isotopes aluminum-26, iron-60 decayed quickly, their energy trapped in rock. It was enough to keep the surface molten for tens of millions of years, a lake of magma hundreds of kilometers deep. Above it, clouds of silicate droplets condensed and rained down again, a storm of stone. When the energy finally began to leak outward, the world exhaled. Steam thickened, cooled, and fell as rain, the first real rain, dropping into seas of lava and vanishing in hisses of vapor. For ages it repeated boil, rain, boil again until the outer crust, cooling unevenly, hardened into plates that cracked and moved like slow glass. Beneath those plates, convection stirred. Rising plumes of heat pushed basalt upward. Cooler slabs sank. This, the beginning of plate tectonics, set the long rhythm that still moves continents today. Every subduction carried trapped water and carbonates back into the mantle. Every eruption exhaled them again. In that loop lay Earth's first balance, a primitive carbon cycle humming beneath a sky too thick to see through. Volcanoes gave, weathering took. The planet learned to breathe. Evidence survives in crystals older than continents. Tiny zircons, dated to about 4.4 billion years, carry oxygen isotopes that speak of liquid water. That is proof enough that oceans existed even while sunlight was weaker. Volcanic warmth and greenhouse gases kept them fluid beneath the dim star. Water, vapor, and carbon dioxide wrapped the globe, trapping infrared light and lifting the air just enough for seas to remain liquid. It was a delicate equilibrium, a faint sun balanced by a thick blanket of gas. The moon hung much nearer then, a looming lantern over molten seas. Its gravity pulled tides across the half-formed crust, drawing energy from Earth's spin and stirring the new oceans. Those stronger tides kept chemical gradients alive, washing minerals over basaltic shorelines and into the steaming basins. Every ebb and surge mixed elements that would later form organics. Though life was still far away, its laboratory was being built in rhythm and tide. Above the water, the sky glowed orange and violet with dust. No oxygen yet, no blue. Ultraviolet light split water molecules high in the stratosphere, but free oxygen never lasted. It reacted instantly with iron and volcanic gases, vanishing into rock. The atmosphere was a restless cauldron, mostly nitrogen and carbon dioxide, laced with methane and sulfur compounds. Each molecule carried heat differently, each one shaping the early climate in subtle ways. Methane, though scarce, magnified warmth. Carbon dioxide held the base layer of stability. Without them, the young oceans would have frozen beneath the dim star. Impacts continued for hundreds of millions of years. The late heavy bombardment left scars deep as mountains and wide as seas. Each collision briefly erased the climate, vaporizing oceans and shattering crust, yet water always returned. Steam condensed, rain fell, and new basins filled. That persistence marked the first real climate feedback, a system that could recover, rebuild, and find temperature again. Volcanoes replenished gases, weathering drew them down. Even then, the dance between heat and cool had begun the same cycle that steadies our world today. The chemistry of that time was violent but precise. Silicate weathering consumed carbon dioxide, locking carbon into carbonate minerals. Each reaction cooled the air slightly, a slow counter to volcanic exhalations. This interplay of degassing and drawdown created the planet's first thermostat. No hand tuned it. It arose from physics alone. The balance of magma, water, and sky produced the earliest climate break, a mechanism that prevented runaway heat or endless freeze. It was imperfect, but it worked well enough for oceans to survive and deepen. In the stillness between bombardments, clouds thickened and storms rolled across a crust newly solidified. Mountains of basalt rose and wore away, feeding minerals into boiling seas. No continents yet, no green, only the endless dialogue of rock and water. Every drop of rain carried acidity. Every river, though nameless, carved its path into stone that would someday cradle continents. The atmosphere shimmered with silvery haze, a mix of droplets and dust. When lightning tore through it, nitrogen oxides formed tiny sparks of chemistry that would later feed life. For now, they were only hints, seeds scattered across a barren canvas. This was Earth's first climate age, the age of fire giving way to steam. From incandescent beginnings, the planet cooled enough to hold oceans without boiling them away. The crust thickened, the air thinned slightly, and sunlight found reflection on liquid water for the first time. No blue skies yet, but a world learning how to breathe through storms. Each process, impact, eruption, rainfall, weathering, was part of a single conversation about balance. And through that long dialogue, the planet transformed from a furnace into a cauldron where stability could at last take hold. In the faint glow of a young sun, the world exhaled steam instead of flame. What began as fire had learned to flow. A soft shimmer lies over the primeval ocean, like starlight caught in a breath. Beneath it, the world of the Archean turns in silence, a planet just beginning to cool. Its crust thin and restless, its skies dim under a sun still young and pale. 4 billion years ago, sunlight reached Earth at barely 70% of its modern strength. Yet, the seas remained liquid. Warmth came not from brightness, but from breath. The slow, invisible breath of gases that wrapped the planet in their patient heat. Methane, exhaled by ancient microbes and born from hydrothermal vents, mixed with carbon dioxide to build a cloak strong enough to hold the chill at bay. It was chemistry that kept the waters from freezing, a greenhouse sky above a simmering sea. The paradox of the faint young sun rests here, quiet and solved by time. With less light to work with, Earth's air found its balance in excess. Carbon dioxide rose high, unchecked by continents that had barely begun to form. Fewer mountains meant less rain to grind them down, less weathering to trap carbon into stone. What escaped volcanoes lingered in the air, thickening the greenhouse, softening the sunlight. Around the edges of this heat, methane added its deeper tone, a molecule both fragile and strong, vanishing under oxygen, yet thriving in its absence. It was the perfect gas for a world not yet blue, a world that breathed through stone and vent, through microbes clinging to the crust. Across this half-dreaming ocean, life had already arrived, small and unseen. In shallow waters, microbial mats spread over sand and rock, weaving filmy skins that trapped sediments grain by grain. With time, those layers hardened into stromatolites, living architecture shaped by light and patience. They fixed carbon, built films of organic matter, and buried it beneath themselves. In doing so, they began one of Earth's oldest rhythms, removing carbon from the air, locking it into rock, and teaching the planet how to breathe. In cycles, the Archean world was not silent after all. It hummed with invisible work. Beneath the sea, hydrothermal vents pulsed with minerals and heat. Water sank into cracks, met molten rock, and rose again rich with iron, nickel, and sulfur. These were the ocean's first nutrients, rising like smoke and spreading through the early seas. Iron, abundant and dissolved in the anoxic waters, drifted freely until small patches of oxygen appeared. Where they met, iron fell as rust, thin layers settling one atop another. Over time, they built banded iron formations, red and gray stripes recording the first hesitant whispers of oxygen. Each stripe a testimony that life had begun to alter the chemistry of the world that made it. The sun's faint glow meant the skies could change quickly with small shifts in gas. When methane built too high, ultraviolet light turned it to haze, orange veils that shaded the surface and cooled the sea. At times, that haze thickened, spreading like a memory of Titan skies. At others, it thinned to clarity, letting warmth return. The climate teetered between greenhouse and shadow, balanced by the pulse of chemistry. No age before or since has walked such a narrow bridge between heat and cold for so long. Days were shorter then. The moon, closer to Earth, pulled harder on the tides. Each sunrise came only 15 hours after the last. The oceans mixed faster, stirred by tides that ran high across the basaltic seafloor. That energy nourished the shallow shelves where microbial colonies grew, keeping nutrients in motion, never letting stagnation take hold. The world's pulse was faster, its nights briefer, its balance fragile but held. Continents began as hints, island arcs, and small cratons cooling from magma, lifting above the restless sea. With their rise came a new chemistry, the slow weathering of granite, a sink for carbon dioxide that began to tug at the greenhouse's edge. As land expanded, the planet's thermostat learned restraint. The carbon cycle closed its first loop. Volcanoes gave, rain took, rivers carried, and the sea stored. Life joined that loop, exhaling and burying carbon, tightening the bond between rock, air, and cell. By the late Archean, the pattern was clear, even if the players could not yet name it. Heat flowed from the core, gases drifted skyward, rain carved stone, and life answered in its quiet, photosynthetic way. The seas glowed faintly with microbial light, not luminous, but alive. The atmosphere held no oxygen yet, but its story had begun to bend toward it. For the first time, biology and geology moved together, one shaping the other, both setting the stage for everything that would follow. The planet's warmth, born from methane and carbon dioxide, was gentle but persistent. The air shimmered with hydrocarbon haze, the seas steamed in twilight, and the continents, few and small, looked like seeds waiting to grow. Nothing hurried, everything learned balance. The Archean ended not with violence, but with deep preparation, a steady intertwining of carbon, water, and light that made oxygen possible, and through it, the long climb toward the world we know. Somewhere in that half-lit sky, the first true dawn rose through haze and mist, touching oceans that breathed warmth without sunlight's strength. The earth was young, its heart hot, its seas alive, its air full of beginnings, and all of it, every shimmer, every ripple, every faint pulse of gas, whispered the same slow truth that life and planet were already learning to keep each other alive. The planet has grown quiet under a pale sun, its breath slowed, its color dimmed. Around 2.4 billion years ago, the air began to change. What had once been a world of iron seas and methane skies shifted toward something sharper, cleaner, and far more consequential. The Great Oxygenation Event, soft in its beginning, profound in its end, unfolded over tens of millions of years, transforming both climate and life. The story is one of chemistry made visible, of a sky learning to breathe. Long before this threshold, photosynthetic microbes had already been releasing oxygen into the oceans. They lived in shallow waters, mats of cyanobacteria spreading like soft films across sunlit shelves. Their photosynthesis split water and released oxygen as a byproduct, but the new gas did not linger. Iron dissolved in seawater drank it in, forming rust-red precipitates that sank as layers of banded iron formations. Volcanic gases rich in hydrogen and sulfur reacted with oxygen too, drawing it down before it could escape to the air. These sinks kept the world in balance, low in free oxygen, high in methane, and warm enough for liquid seas, despite the faintness of the young Sunday. But even constant appetites have limits. Over time, the sinks filled. Iron in the oceans diminished, volcanic output slowed, and the oxygen that once vanished began to accumulate. Slowly, invisibly, the atmosphere tipped toward a new state. Methane, once dominant, met its chemical rival. Oxygen oxidized it into carbon dioxide and water vapor, erasing a greenhouse gas hundreds of times more potent. The air cleared, but the warmth fled with it. Temperatures dropped, and ice crept outward from the poles. By about 2.4 billion years ago, glaciers had reached deep into the continents. Some evidence suggests the ice may have spread nearly to the equator, turning the Earth into a pale, reflective orb. This Paleoproterozoic chill was not a sudden winter, but a long, slow contraction of warmth. As snow and ice expanded, their bright surfaces bounced sunlight back into space, amplifying the cooling through albedo feedback. Continents newly assembled near the equator lifted highlands into colder air, where snow persisted year-round. The planet entered a state of deep equilibrium, an uneasy quiet where light fell, but little warmth remained. For millions of years, ice and oxygen ruled together, twin consequences of the same invisible chemistry. In the oceans below that frozen crust, life adapted. The anaerobic microbes that once thrived everywhere retreated into sediments and hydrothermal refuges. Others, those that could tolerate or even use oxygen, began to expand. The metabolic revolution had begun. Oxygen offered power. One molecule could yield more energy from the same food. It also brought danger, for its reactivity could break apart the delicate molecules of life. Evolution responded by inventing defenses, enzymes like catalase and superoxide dismutase that still protect every living cell today. The first antioxidant shields were forged in that ancient cold. Above, the new atmosphere altered the light itself. Oxygen in the air formed ozone in the stratosphere, a thin but potent barrier that absorbed ultraviolet radiation. The surface world, once bathed in sterilizing rays, grew gentler. The sky's color shifted subtly, and with it the chemistry of the oceans below. Iron, now oxidized and insoluble, settled out. The great iron formations dwindled and vanished from the geologic record. In their place came red beds, rusted soils that spoke of oxygen's permanent arrival on land. Carbon isotopes too began to wander, recording the rearrangement of the global carbon cycle as burial, weathering, and volcanic release found new balance. Volcanoes never slept entirely. Even through ice, they breathed carbon dioxide into the air. Over millions of years, that steady outgassing began to accumulate. Cooler temperatures had slowed silicate, weathering the process that draws CO2 down so carbon dioxide rose. Slowly, the greenhouse returned. The ice retreated, first in isolated valleys, then across continents. Earth thawed, and the climate regained its fluid rhythm. Oxygen remained, but now tempered by feedbacks that would define the rest of planetary time. Volcanism, adding heat, weathering, subtracting it, biology, responding in the space between. The great oxygenation event was less a moment than a transition, a slow symphony between rock, air, and cell. Its music echoes in every breath today. Oxygen changed the redox balance of the planet, opened new metabolic doors, and set the stage for multicellular life. But it also taught the Earth restraint. Chemistry, once simple, became recursive. Every gas influencing temperature, every temperature influencing gas. The biosphere and the atmosphere became partners in feedback, bound forever in mutual control. When we breathe now, we participate in that ancient negotiation. The chill that once locked the planet in ice is long gone, but its lesson remains that even the gentlest molecule can tip the balance of worlds. Life reshaped its own sky, and in return, the sky reshaped life. Oxygen and ice together marked the Earth's first true climate age, a time when the planet learned how fragile warmth could be, and how persistence could carve beauty even from frost. The world, long frozen beneath a Paleoproterozoic hush, begins to breathe again. Glaciers that had wrapped the continents loosen their grip, leaving behind a raw skin of rock. As sunlight spills across that scarred surface, rain falls for the first time in long silence, washing fragments of new minerals into waiting seas. Carbon dioxide, once drawn down by ice and still rising from patient volcanoes, gathers in the air again. The greenhouse curtain thickens, not wild, not sudden, but steady, and warmth returns to the surface like a memory finding its way home. This renewal is marked in stone. Across the planet's old cratons, a peculiar layer tells the story. Thin layers of limestone capped the old ice deposits, marking the planet's relief. They are the geological sigh of relief after global chill, evidence that once the ice melted, weathering raced to life. Fresh rock, ground fine by glaciers, met the warm rains. Calcium and bicarbonate flowed into the oceans in torrents, combining to form these distinctive carbonate beds. Each crystal is a record of the first great planetary exhale after suffocating cold. In the oceans, stratification began anew. Surface waters, heated by the growing sun, grew lighter, while deeper layers held salt and cold. Winds mixed them unevenly, shaping the first modern-style circulation. Evaporation and rainfall once again danced across continents. Rivers carved paths, and the hydrologic cycle muted during the long ice-found rhythm. These oceans, no longer sealed under global ice, allowed gases to exchange more freely. Oxygen, now a persistent though modest trace in the air, spread more deeply into the sea. Life responded quietly. Microbes adapted to this low-oxygen world, evolving enzymes and metabolisms that used it efficiently without wasting energy. It was not abundance yet, but endurance, proof that complexity could root itself in balance. Volcanoes continued their slow chorus. Carbon dioxide from deep sources entered the atmosphere faster than it was consumed. But the Earth, already learning its own rhythms, built a thermostat from stone. As temperatures rose, rainfall increased, and chemical weathering quickened on exposed silicate rocks. These reactions locked carbon into new minerals, pulling it from the sky and cooling the planet again. When the surface cooled too much, weathering slowed, letting volcanic gases accumulate once more. In this seesaw lay the secret of climate stability, a feedback measured not in centuries but in the quiet patience of millions of years. The planet, for the first time, held a conversation with itself. This balance was not perfect. The memory of ice remained. Smaller glaciations still visited high mountains and polar shores. But the great planet-wide freeze no longer returned. The atmosphere had found its middle ground: carbon dioxide, enough to keep the seas liquid, oxygen enough to sustain new metabolisms, and sunlight bright enough to drive photosynthesis without searing. Methane, once the chief greenhouse partner, dwindled as oxygen oxidized it into carbon dioxide and water. The sky changed color, thin haze clearing into a softer blue. Soils reddened as iron met oxygen for the first time, recording the shift from a reducing world to one that breathed oxidized air. In ancient paleosols, scientists still trace this turning point for the Earth's slow decision to become more open to life. Continents drifted through shallow oceans, reshaping air and sea currents as they went. When they gathered near poles, ice advanced again, sculpting brief returns to cold. When they spread toward equatorial warmth, meltwater filled basins, and tropical storms drew energy from warm seas. Tectonics became climate's silent composer. Mountains rose and wore away. Erosion fed minerals to the ocean, changing its chemistry grain by grain. Each uplift and collapse, each drift of land, added another verse to the long song of carbon and heat. Through all these changes, life remained small but steadfast. Stromatolites, layered colonies of cyanobacteria, flourished in the shallows, releasing oxygen in quiet excess. Iron formations waned as the oceans turned less anoxic. Rust-colored bands gave way to limestones and shales, signs that the planet's chemistry was reaching a more stable harmony. The once hostile surface grew familiar to metabolism. Energy moved through cycles instead of breaking them. The first whispers of food webs began, microbial, but connected an unseen architecture of cooperation that mirrored the planet's own balancing act. The Earth's temperature settled near a new normal, perhaps warmer than today's, but tempered by feedbacks that would echo through every future epoch. The crust itself, cracked by ancient tectonics, served as both memory and mechanism. From volcanic arcs to continental shelves, the exchange between deep and shallow, hot and cool, fast and slow, created a home for persistence. The chaos of youth gave way to moderation. This was no return to purity, but an evolution toward equilibrium. In that balance, the seeds of habitability deepened. Shallow seas gleamed beneath thin clouds, and light filtered softly through them, feeding mats of microbes that fixed carbon and nitrogen. These were the first long, stable afternoons of Earth, the first climate calm enough to be predictable. And in the stillness of those ancient waters, something remarkable happened. The planet began to keep time. Ice and fire no longer ruled by impulse. They took turns with rhythm. The carbon cycle became a pulse. The tides traced their loops without interruption. Even the rocks recorded seasons in thin laminae, delicate stripes of stability. The age after the Great Oxidation was neither storm nor silence. It was the long, slow inhale between them, a world recovering its warmth, learning restraint, and setting the pattern that would guide every climate that followed. The planet, at last, had learned to breathe in peace. The world lies wrapped in ice, a nearly complete mirror, turning sunlight back into space. It is the cryogenian, between 700 and 635 million years ago, when Earth nearly lost its colors beneath endless white. Two long glaciations, the Sturtian and the Marinoan, reached far beyond the poles. Ice pushed across the equator, glaciers floated in tropical seas, and continents vanished under miles of frost. Dropstones, pebbles carried by icebergs and dropped into fine marine mud, now mark that impossible reach. They rest like whispers of frozen time, proof that even the warmest latitudes once held winter. Cooling began slowly, a gentle dimming of warmth. Continents sat in strange positions, clustered near the equator, where heavy rainfall and rock weathering pulled carbon dioxide from the air. With less greenhouse gas to trap heat, oceans began to chill. Sea ice formed and brightened the planet's surface, reflecting sunlight and deepening the cold. This ice albedo feedback grew stronger with every degree of cooling, until the balance tipped a feedback loop that no small warmth could stop. Oceans thickened with ice, tens of meters deep. Glaciers ground mountain ranges down to pale bones. Beneath the frozen lid, volcanic arcs continued to breathe, releasing carbon dioxide into a sky too still to recycle it quickly. Even in such extremity, the planet lived. Volcanic warmth cut small refuges into the shell of frost pockets of liquid water that steamed upward, feeding thin microbial films. Near hydrothermal vents, ecosystems survived by chemical energy alone, far from sunlight. Along fracture zones, open water formed polynyas, where wind or currents kept surfaces clear. In those narrow openings, light reached down just far enough for photosynthesis to persist. Biomarkers preserved in ancient sediments confirm it. Chlorophyll's chemical descendants, traces of green in a white world. Life reduced itself, but did not vanish. It waited, patient, and unseen, inside the breath of stone. The glaciations lasted millions of years. Oceans beneath the ice grew dense and stratified. Carbon and nutrients accumulated in the deep. Over time, volcanic gases thickened the atmosphere with carbon dioxide, rising drop by drop through trapped vents. Without rain or rivers to draw it back into rock, the gas built unchecked. Then, as greenhouse strength reached its threshold, balance inverted once more. The mirror shattered. Deglaciation came not as a thaw, but as a flood of light. Within only tens of thousands of years, an instant to geology, the frozen lid gave way. Greenhouse heat surged through clear skies, melting ice into torrents. Meltwater poured into basins, eroding mountains newly freed from their burden. Oceans rose in chaos, and then calmed, carrying dissolved minerals that built the next great marker in stone, the cap carbonates. These smooth, pale layers rest atop glacial deposits around the world, testimony to a sudden swing from deep freeze to warmth. Their chemistry tells of an atmosphere thick with carbon dioxide and seas fizzing with calcium and bicarbonate, the ingredients of rebirth. As ice retreated, oxygen and carbon mingled in renewed cycles. Weathering returned. Rivers carried fresh nutrients to the sea. Photosynthetic life bloomed again, feeding the slow rise of oxygen that would later shape animals. The ocean's stratification broke, mixing the deep with the surface. Trapped carbon escaped, and new chemistry rewrote the water column. The world, exhausted by cold, breathed again. Yet the cryogenian left scars that time still reads. Striated rocks in Namibia and Canada, glacial pavements in Australia, chemical signatures in China, all tell the same story. Ice that reached the tropics, and a recovery fierce enough to erase it. The memory lives in isotopes of carbon, oxygen, and strontium, each ratio a line of testimony. They show swings so large that no local climate could explain them. Only a planet-wide freeze fits the rhythm. The idea of a snowball Earth once seemed fantasy. How could life endure a world sealed in frost? But data after data aligned. The sediments spoke, the chemistry agreed, and the survival of microorganisms proved that even the harshest ages are temporary. The cryogenian revealed both fragility and resilience, how small changes in orbit, rock, and air can decide the fate of oceans, yet how volcanic breath and patient biology can restore them. When the last glaciers melted, the Earth shone blue once more. Sunlight met open water, clouds drifted freely, and the air thickened with new promise. The cycle had completed, cold, giving way to warmth, dormancy yielding to bloom. From this balance of extremes came the conditions for complex life, the quiet preparation for the Cambrian dawn that would follow. The Snowball Earth remains a reminder whispered through stone. Even silence can end in song. Even ice can remember how to melt. A thin veil of silver light spreads across the sea, as if the planet itself exhales after holding its breath for too long. The ice that once encased it softens and flows away, leaving behind a world newly awake. This is the Ediacaran age, a time when Earth learned to breathe again, not in sighs of carbon or methane, but in oxygen, slow and sure. The air grows patient, the oceans turn mild, the planet shifts from survival to growth. After the cryogenian, when glaciers had reached the equator and light could barely touch open water, warmth returns. Carbon dioxide, built up from long volcanic silence beneath the ice, now traps enough heat to thaw the seas. Meltwater pours from cliffs of ice into salty basins, layering the ocean with fresh and heavy currents. The change leaves its fingerprints in stone. Cap carbonates thick, pale deposits of calcium and magnesium laid down rapidly after the glaciers vanished. They mark a planet in recovery, breathing deeply for the first time in tens of millions of years. As the seas mix, nutrients flush outward from land, newly exposed to weather. Rain falls on bare rock for the first time in ages, breaking it into mineral dust rich in phosphorus and iron. Rivers carry those gifts to the margins of continents where life, still microscopic but restless, drinks them in. With each cell that grows and dies, carbon is locked away in mud or dissolved into deeper water. That burial quietly tips a balance. Less carbon dioxide remains in the air, more oxygen gathers above. It is not a single leap, but a staircase, each step carved by time and chemistry. Oxygen rises in pulses, tracked now by the ratios of sulfur and carbon isotopes in ancient layers. The numbers show oscillations, brief stalls, then surges like the slow rhythm of lungs filling and emptying. In these surges, the oceans become habitable in ways they had never been before. The threshold crossed somewhere between 1 and 10% of modern oxygen, but even that modest climb was enough to allow large, soft bodies to endure. The first visible animals' discs, fronds, quilted mats pressed into Ediacaran sands appear. Their forms seem alien. No shells, no bones, only impressions of folds and ripples. Yet they tell a story of energy newly available. Oxygen means movement, metabolism, the ability to grow beyond a single cell's reach. In the shallow seas, these organisms spread like gentle constellations on the ocean floor. Ranger morphs unfurl fractal fronds that gather nutrients from water rather than light. Others, like Dickinsonia, creep slowly, leaving faint trails in microbial mats. They are not predators yet, but they are complexity incarnate, proof that the biosphere has crossed another boundary. Where before the planet's climate ruled life absolutely, now life begins to whisper back into the climate. Biotubation, the act of animals stirring sediment, begins quietly here. Tiny burrowers oxygenate the seabed, changing how organic matter decays. Where once the seafloor sealed its carbon into black shales, now that carbon oxidizes and returns to the air. It's a subtle but powerful feedback. Oxygen encourages life. Life rearranges carbon. Carbon modulates temperature. The loop closes, and the system steadies. Earth, for the first time, regulates itself through living breath. Meanwhile, the continents drift in slow ballet. Gondwana gathers in the south. Laurentia drifts nearer the equator. Their positions sculpt ocean currents, guiding heat like invisible ribbons through water. Circulation strengthens after the ice retreats, mixing surface and depth, distributing warmth and gases more evenly. Monsoon patterns begin to stir along continental edges, creating regional climates and zones of productivity. The polar regions remain ice-free for long spans, though seasonal frost may visit the shadows. Sea levels stand high, flooding wide continental shelves, where sunlight and nutrients meet perfect nurseries for new ecosystems. The greenhouse remains modest, not the runaway of earlier eons, nor the deep freeze of Snowball Earth. Carbon dioxide continues to decline as weathering of silicate rocks and biological uptake remove it. With a calmer sun and a balanced sky, temperature settles into gentle oscillation. The Ediacaran world is a cradle of equilibrium, fragile, but real. Fossils from this time are both evidence and poetry. They show no bones, no teeth, only the faint geometry of soft tissues pressed into silt. Yet those shapes reveal what physics allows. With higher oxygen, diffusion supports larger bodies. With nutrients, metabolism expands. Some creatures anchor to the seabed, others float or crawl. They live in colonies, in layers, in slow rhythms that echo tides and sunlight. When storms roll through, they are buried. When calm returns, new generations spread again. Each burial is a page, each impression a line in Earth's long diary of breath. Above them, the air thickens slightly with oxygen, transforming the color of sunsets, deepening the blue of sky. Fire, for the first time, becomes possible in theory, though forests do not yet exist to burn. Lightning still dances over barren land, but the stage is set for future blaze. The chemistry of the atmosphere is moving toward modernity, one molecule at a time. Phytoplankton evolved too, from simple mats to cells with tougher walls and heavier minerals. Their sinking speeds increase, drawing carbon to the deep ocean more efficiently. The biological pump, as modern science calls it, begins its long work here. Each descent of dead plankton buries a fraction of the sun's energy, cooling the air above. The dance of photosynthesis and burial becomes the silent governor of climate. By the close of the Ediacaran, oxygen reaches perhaps 15 to 20% of modern levels, enough to sustain complex food webs and skeletal forms that soon appear in the Cambrian. The planet that had once frozen solid now hums with stability. No global ice lids, no runaway heat, just the calm oscillation of a self-tuned system. Gases, rocks, and biology share control. From the molten past to this tempered greenhouse, Earth has learned balance through suffering. In this steadiness lies beauty. The world has endured extremes, oceans of fire, eons of ice, and now rests in a middle tone, warm enough for life, cool enough for oceans. The creatures drifting through its shallow seas do not know what they represent, but through them, the planet begins its long dialogue between climate and consciousness, setting the first conditions for everything that will someday look back and remember. A quiet wind passes over the sea. Ripples move outward, soft and certain. The age of recovery continues, one breath at a time. The early Paleozoic world was a planet of shallow seas and warm tides, its continents scattered like islands across a broad, breathing ocean. Carbon dioxide filled the air more thickly than in any human age, to come nearly 10 times modern levels. And under that greenhouse sky, warmth pooled across the surface. The poles were mild, the tropics rich with light. On continental shelves, sunlight reached the seabed, feeding mats of algae that laced the water with oxygen. In these quiet lagoons and open shallows, the Cambrian and Ordovician life forms multiplied. Trilobites walked the mud, graptolites drifted, and soft corals fanned the current. The seas shimmered not with color but with promise, a laboratory of forms where bones and shells first learned to exist. Across the low continents, seas flooded broad, flat plains. These were eperic seas, shallow, sunlit, and alive. Ocean currents spread heat from the equator outward, softening every season. Calcium and carbon cycled through these waters, locking greenhouse gases into limestones that would later rise as mountains. The circulation was gentle, global, and slow, a rhythm guided by the planet's rotation and the distribution of land. Warmth was not evenly spread, but endlessly redistributed, making even high latitudes hospitable to life. It was an age of expansion, of stable warmth and thriving oxygen, where complex ecosystems could build upon themselves. Yet even the most patient equilibrium begins to tilt. Over millions of years, the slow engines of tectonics rearranged continents, and weathering began to pull carbon dioxide from the air. Mountain belts rose, their fresh rock faces drawing in the gas through chemical reactions with rainwater. Each drop that fell, each grain that washed away, took a trace of carbon with it, sequestering it as carbonate in the ocean's floor. The effect was slow but cumulative, a planetary inhale that cooled the breath of the world. Silicate weathering, quiet but relentless, became the hand that dimmed the warmth. As the greenhouse weakened, ice found its opportunity. Around 445 million years ago, the southern supercontinent of Gondwana drifted near the South Pole. There, sunlight came at low angles, and long winters deepened. With reduced carbon dioxide, the air could no longer hold its heat, and glaciers began to form. The Hernantian glaciation, named from a Welsh valley, grew across the highlands of what is now Africa and South America. Vast ice sheets spread outward, scouring rock, carving valleys, and locking away ocean water. Global sea levels dropped by more than 100 meters. Shallow seas that had once covered continents drained, leaving coral reefs stranded and ecosystems gasping for continuity. The evidence of this cooling lies written in stone and isotope alike. Rocks from ancient shorelines show dropstones, pebbles carried far from land by icebergs and released into marine mud when the ice melted. Oxygen isotope ratios within fossils tell the same story. Waters turned colder, and ice volume expanded. Even carbon isotopes record the rhythm, showing spikes from organic matter burial that briefly starved the atmosphere of its greenhouse gases. Every data point, in its silent way, confirms the same global choreography, Earth drawing itself into a deep, reflective calm. But glaciation was never the whole story. It was a pulse, not a state. As the ice thickened, silicate weathering slowed under the frozen crust. Volcanic outgassing continued beneath, feeding carbon dioxide back into the air. The feedback turned, slowly, inevitably. Within a few million years, the ice began to retreat. Meltwater rushed into the seas, and shorelines crept upward again. Sediments shifted, ecosystems scrambled to reassemble themselves, and warmth returned like a remembered song. The recovery, though slow, carried resilience. Earth's climate, perturbed but not broken, finding its balance again between carbon sources and sinks. The Hernantian extinction, one of the great losses in Earth's record, marked the price of that instability. Roughly 85% of marine species vanished, most from shallow habitats that had been the nurseries of complexity. As temperatures dropped, oxygen levels in water fell, circulation patterns changed, and ecosystems fragmented. The very seas that had cradled the Cambrian explosion became graves for their own abundance. Yet from that silence, new forms would later emerge, adapted to colder currents and shifting tides. Every lever of climate played its part. Greenhouse gases, albedo from ice and cloud, ocean currents shaped by the drifting continents. Together they form a self-regulating system, fragile in the moment, resilient in the long view. The early Paleozoic story is not one of disaster, but of equilibrium rediscovered. A brief ice age cooled the fervor of a greenhouse world, only to yield once again to warmth. In that oscillation, the planet learned how to balance its own heat, how to breathe between fire and frost. And still, the sediments keep their quiet record layers of limestone and shale, rich in fossils that once basked under Ordovician sun or shivered under glacial light. Each stratum carries both memory and evidence that life and climate, in partnership and conflict, have always shared the same tide. Somewhere in those stones lies a rhythm. We still follow the rise and fall of warmth, the patience of recovery, the truth that even ice can melt back into calm seas. Mist lingers among trunks that have only just learned to stand. The air is heavy, rich with the scent of wet soil and strange new life. In the deep Devonian world, green had finally found its courage. For the first time, continents were no longer bare rock and algae-streaked shallows. They were threaded with ferns, club mosses, and early trees, whose roots reached down like questions into the cooling crust. Each root broke stone into sand and clay, opening fresh surfaces to the sky. That simple act, roots biting rock, changed the atmosphere forever. Silicate minerals weathered faster, binding carbon dioxide into solution. Rivers, once sterile ribbons, now carried bicarbonate ions toward the seas, where they settled as carbonates on the ocean floor. In that quiet chemistry lay a planetary turning point. Carbon, once drifting freely through air, began to hide in stone. The drawdown softened the warmth that had wrapped Earth for eons. The Devonian world cooled not quickly, but with patience, each rainfall washing more carbon from sky to sediment. Forests deepened their reach. Trunks rose several meters high, shaded canopies dimmed the ground, and decay began to form rich black soils. Buried beneath silt and time, that organic matter locked away what sunlight had built. Photosynthesis took in carbon dioxide and released oxygen. Burial kept the carbon from returning. The slow arithmetic favored air more breathable, seas more alkaline, and a climate inclined toward chill. But balance rarely comes without consequence. Nutrients washed from forested hills into shallow seas, fueling blooms of algae. Their deaths thickened the water with decay, stripping oxygen from the depths. Some basins turned anoxic, dark and heavy with sulfur. Fish and corals struggled, many vanished. The late Devonian extinction came not from fire or asteroid, but from the quiet suffocation of ecosystems overwhelmed by their own fertility. It was an age of abundance, tipping into absence, a reminder that life's triumph reshapes the world that nurtures it. Still, the pattern endured, roots breaking stone, rivers carrying memory to the sea. Through that process, climate cooled enough that by the Carboniferous period, ice returned to Gondwana, the great southern continent. There, across what are now South America, Africa, and Antarctica, glaciers advanced and withdrew in slow rhythm. Sea levels rose and fell with each pulse, carving repeating patterns of sandstone, shale, and coal. The cyclothems, Earth's heartbeat written in sediment. The coal itself was the forest's afterimage. Vast swamps spread across equatorial plains, dense with lycopsids and ferns taller than houses. In stagnant water, fallen trees did not fully decay. Instead, they sank into peat, layer upon layer. Over millions of years, heat and pressure turned that peat into coal, sealing away gigatons of carbon. The atmosphere above, deprived of what burning would have returned, filled with oxygen instead. Levels rose to more than 30% higher than any time since. Air so rich made breathing easy for insects and amphibians. Giant dragonflies with wings nearly a meter wide ruled the air. Millipedes longer than a human body wandered the forest floor. Yet that same oxygen turned dry seasons dangerous. Fires, once rare, became frequent. Lightning could ignite whole forests, and flames, fed by fuel and air, burned hotter and longer than ever before. Even so, new life adapted. The green world had learned to cycle through growth and ash, through wet, calm, and dry blaze. Meanwhile, the continents were slowly converging. Tectonic drift drew the scattered land masses together into a single immense supercontinent Pangaea. As the plates met, mountains rose in vast folds. The Appalachians, the Urals, ancestors of today's ranges. These ridges deflected wind and rainfall, reshaping the global climate again. Along Pangaea's coasts, monsoons poured across lush floodplains, feeding rivers that braided through ferns and moss trees. Farther inland, beyond the reach of ocean moisture, deserts spread under a harsher Sunday. The contrast between green margins and dry heart sharpened, a pattern that would echo through later ages. Ice advanced and retreated over Gondwana in repeating cycles. Glacial striations scored the rocks of South Africa and India, proof of frozen ages beneath their present warmth. Each cycle traced a rhythm governed by orbital variations. the subtle changes in Earth's tilt and path that alter sunlight's distribution. These Milankovitch rhythms, as we call them now, pulsed through the Paleozoic like a quiet drumbeat, ice swelling when summers cooled, melting when they warmed. Vegetation amplified the signal. When forests expanded, they drew down carbon dioxide, deepening glaciation. When glaciers grew, they exposed bare rock that slowed weathering, allowing carbon dioxide to rebuild. In this feedback, ice and plant held conversation, a slow dialogue across continents. For tens of millions of years, that equilibrium held. The late Paleozoic Ice Age was not a single freeze, but a long, breathing pattern of cold and thaw. During glacial intervals, sea levels fell, exposing broad coastal plains. During melts, those plains drowned again beneath shallow seas rich with life. Sedimentary records show each breath clearly: coal, shale, limestone, layer upon layer, like pages in a planetary diary. Eventually, the balance shifted again. Volcanic outgassing from rifting crust returned carbon dioxide to the air, slowly saturating the weathering feedback that had kept climate cool. As concentrations rose, glaciers receded, leaving behind valleys polished by ancient ice. Warmth crept back over the continents, and the long reign of carboniferous forests began to fade. New ecosystems took their place, more open and arid, seeded by reptiles that no longer needed water to breed. The Devonian Carboniferous world had shown how deeply life and climate intertwine. Roots and rain, oxygen and stone, each depended on the other. When forests grew, the planet exhaled oxygen and cooled. When they shrank, warmth returned. Even in silence, this partnership continued, carbon flowing from air to leaf to soil, then locking itself in rock. The lesson was written not in catastrophe but in endurance, the earth learning to regulate itself through living skin. If you close your eyes, you can almost hear that balance hum beneath the wind. The whisper of roots splitting basalt, the soft crackle of fern fires under high oxygen skies, the sigh of glaciers sliding over continents. It is the sound of the planet adjusting its breath, finding the pace between fever and frost. And somewhere in that rhythm, the world learned what it meant to stay alive for ages. A wavering mirage rises above hot stone, the air shimmering with its own exhaustion. It is the late Permian, more than 250 million years ago, and Earth is restless beneath its crust. Deep within what is now Siberia, a fracture opens in the planet's skin. For millions of years, molten rock surges upward in waves, lava flooding plains, fire painting the horizon. The eruptions build a vast igneous province, thousands of kilometers wide, one of the largest volcanic events in the history of life. From those endless fissures come gases that change the air itself: carbon dioxide, sulfur dioxide, and fine volcanic ash that drifts across the planet like breath held too long. The atmosphere thickens with carbon. Carbon isotopes recorded in rocks show a sharp downward shift, a signal that too much carbon has entered too quickly. The source lies partly in the magma's path. It burned through coal seams and carbon-bearing sediments, cooking them into gas. Methane, released from oceanic hydrates destabilized by the heat, adds to the surge. The chemistry is simple but brutal. More carbon dioxide traps more infrared energy. Global temperatures rise by several degrees, perhaps by 10. The oceans warm until they can no longer hold oxygen in the same way. Water that once breathed life begins to suffocate. The seas turn strange. In the depths, oxygen levels plummet. Bacteria that thrive without oxygen take over. Their metabolic byproducts, hydrogen sulfide and methane, creep upward through stagnant layers, poisoning the shallows. Coral reefs dissolve. unable to withstand the acidified waters. Trilobites, the armored icons of Paleozoic seas, vanish after hundreds of millions of years of endurance. Brachiopods, ammonites, and countless small shelled creatures follow. The fossil record marks this boundary as a line of loss, so sharp that paleontologists call it simply the Great Dying. On land, the heat is merciless. Pangaea, a single vast supercontinent, spreads from pole to pole. Its interior, far from the moderating breath of oceans, turns to desert. Monsoon cycles fail, rainfall dwindles. Rivers shrink to braided channels that flash with floods, then dry into salt plains. The red beds of late Permian rock record the iron of oxidized soils baked by drought. Trees shed their leaves and do not return. Whole forests burn or collapse into silence. The landscape becomes sparse, a patchwork of hardy survivors clinging to thin moisture. Atmospheric dust from the eruptions creates short, sharp chills followed by longer, unrelenting warmth. Sulfur aerosols reflect sunlight for a time, but they soon wash out, leaving behind the greenhouse that remains for millions of years. Mercury from volcanic vents settles into sediments, still measurable in rock cores today, confirming the reach of the Siberian Traps's fire. Ocean acidity rises as the carbon dioxide dissolves into surface waters. Shells thin, reefs crumble, and marine productivity falters. When the base of the food web falters, the entire structure comes down. The figures, though ancient, are staggering. Roughly 9 of every 10 marine species disappear. On land, perhaps 7 of every 10 perish. Insects, once resilient, face their first and only known mass extinction. It is not an instant apocalypse, but a drawn-out suffocation, a slow unraveling of systems that once balanced one another. The pace of carbon release overwhelms Earth's natural regulators. Weathering, plant uptake, ocean absorption, all processes that need tens of thousands of years to respond. The injection comes faster than the repair. Yet even in that devastation, the planet's machinery continues to turn. Rain still falls, rivers still carve valleys. The silicate weathering cycle begins its slow reclaiming of carbon. As volcanic activity wanes, the oceans start to draw down the excess gases. It takes millions of years, but the chemistry begins to balance again. With cooling comes new opportunity. Early in the Partis, Triassic, small forests of conifers and ginkgos reappear where the heat once forbade growth. Coral-like organisms rebuild fragile reefs. The survivors diversify into forms that will later define the Mesozoic, the age of reptiles and forests renewed. Climate remains warm during this early recovery, yet the planet is once again steering toward equilibrium. It is a reminder that Earth, though battered, never abandons its feedbacks. The carbon cycle, the water cycle, the slow grinding of plate tectonics. These are its long memory, its way of healing from excess. The mismatch between the quick violence of release and the slow patience of repair is the true lesson written in stone. Sediments from that time still whisper of those extremes. Layers rich in ash tell of eruption after eruption. Bands dark with organic matter trace the suffocating oceans. In ancient soils, paleosols reveal drying climates and erratic seasons, their minerals marking every turn of aridity. The story they hold is not simply of destruction, but of inertia, the time it takes for a planet to right itself after imbalance. Later, as the Triassic unfolds, the Earth will once more experience volcanic episodes. The rifting that begins to split Pangaea will open the first outlines of the Atlantic. Each pulse of lava, each wave of outgassing, will stir the atmosphere again, but never quite as fiercely as that late Permian blaze. The scars of that event remain visible in the fossil record, and in the isotopic ratios of rocks scattered across continents that were once united. And though we call it an extinction, the Permian's ending was also a beginning. It cleared ecological space for new forms to rise, for reptiles to grow large, and for mammals to begin their hidden story in the undergrowth. The biosphere rebuilt itself not by forgetting the catastrophe, but by adapting to its memory. The late Permian world teaches a quiet truth that feels close, even now, that when carbon rises too fast, warmth follows. When oceans lose their breath, life falters. Yet the Earth endures. It turns its own disasters into new beginnings, given enough time and patience. The stones of Siberia still carry the echo of that ancient fire, and the oceans still remember the heat that once ran through them. And as the night deepens around this story, we can feel the weight of that endurance, the slow, measured heartbeat of a planet that burns, recovers, and dreams itself whole again. Warm air drifts like the breath of an ancient forest, thick with green and salt. The Mesozoic world unfolded beneath a sky that never knew frost, its warmth drawn from deep within the planet. From the Jurassic through the Cretaceous, the Earth lived in a greenhouse phase, humid, fertile, and vast. Carbon dioxide filled the air in generous measure, rising from the open seams of ocean ridges and volcanic arcs that rimmed the continents. Sea levels stood hundreds of meters higher than in our time, flooding continental margins with shallow, luminous seas. The polar caps were bare of ice. Forests reached to the poles, their rings recording mild winters that never froze. Across this greenhouse Earth, continents drifted slowly apart. The supercontinent Pangaea, once whole, cracked and divided into northern Laurasia and southern Gondwana. Between the rifted plates, new oceans were born, each one breathing heat and moisture into the atmosphere. The young Atlantic widened with every volcanic pulse, and mid-ocean ridges outgassed carbon dioxide that kept the planet's surface warm. Inland seas spread across low continents, creating vast interior waterways. One of the greatest, the Western Interior Seaway, split North America in two, stretching from the Arctic to the Gulf of Mexico. Warm currents moved through it like blood through an artery, carrying tropical heat deep into temperate latitudes. The warmth was not a fever, but a long equilibrium, an age of balanced excess. Mean global temperatures may have stood 6 to 10 degrees higher than ours. Tropical zones extended far toward the poles, and temperate regions blurred into subtropical forests filled with ferns, cycads, and conifers. In what is now Alaska, fossil wood still holds the pattern of tree rings from forests that once grew under a dim, frost-free Sunday. Dinosaurs roamed these high-latitude groves, enduring long polar nights without hibernation. The absence of ice gave the atmosphere freedom to circulate moisture freely. Clouds built high, rains fell often, and rivers carried minerals to the sea. Yet even in such warmth, the climate was not entirely stable. Beneath the shining seas, oxygen sometimes vanished. The Mesozoic's oceanic anoxic events left behind black shales, dark, fine-grained layers, rich with preserved organic matter. In these intervals, parts of the ocean stopped breathing. Warm surface waters, dense with nutrients, blocked circulation, and oxygen from the upper layers failed to reach the depths. Plankton bloomed and died, sinking into still waters that could not decay them fully. These organic sediments buried carbon that would one day feed the planet again, in the form of oil and gas. Each anoxic event lasted thousands to hundreds of thousands of years, a reminder that abundance and collapse can share the same tide. The mid-Cretaceous, about 100 million years ago, brought the zenith of this long greenhouse. Temperatures at the poles remained above freezing year-round. Crocodiles swam in Arctic rivers. Reefs flourished at latitudes that today would host icy coasts. The air itself carried nearly 4 times the carbon dioxide of modern levels. Yet, even at that extreme, the Earth's natural feedbacks began to whisper restraint. Warmth accelerates weathering, and as tropical rains fell upon new volcanic mountains, they drew carbon dioxide out of the sky. Dissolved in rivers, it flowed into the oceans and settled as limestone on the flooded shelves. This slow process, repeated countless times, began to cool the world, millimeter by millimeter of rock. Deep ocean chemistry changed as well. Calcium carbonate precipitated in steady rhythm, locking away carbon for millions of years. Each shelf of limestone that now crowns a mountain range was once part of that quiet exchange, a geological diary of carbon's passage from air to stone. The planet's thermostat, set by volcanic input and weathering output, worked without hurry but with certainty. By the late Cretaceous, global temperatures began to edge downward, hinting at the cooler patterns that would later dominate the Cenozoic. The life that thrived under this sun adapted to the constancy of warmth. Reptiles reached their greatest variety. Sauropods with necks like cranes, horned ceratopsians, swift raptors with feathers glinting in the light. The seas swarmed with ammonites and marine reptiles, plesiosaurs, ichthyosaurs, and mosasaurs gliding through the green water. Plants mirrored the age's abundance. Ferns and cycads carpeted lowlands, while conifers rose in tall, resin-scented stands. Near the end of the Cretaceous, flowering plants appeared, modest at first, then spreading across every continent. Pollinators followed the earliest bees and butterflies, tracing paths that still define ecosystems today. It was a time of exuberant life, fed by warmth and stability. Still, the ocean held its warnings. Chemical traces in marine sediments show that intervals of anoxia returned again and again, sometimes linked to bursts of volcanism or changes in ocean circulation. Each pulse marked a disturbance in the carbon cycle, a reminder that the same processes that give life can also threaten it. Yet recovery followed each collapse, as weathering and biological productivity rebalanced the system. Earth's resilience worked through chemistry and time, not intention. As the Cretaceous drew to its close, long-term cooling continued. Mountain building altered weathering rates, and seafloor spreading slowed, reducing volcanic carbon release. The greenhouse remained, but its peak had passed. Then came the sudden interruption, the impact near Chicxulub that ended the age of dinosaurs. The collision itself was not part of the planet's slow climate rhythm, but it reset ecosystems across land and sea. The atmosphere dimmed, temperatures fell sharply, and in that pause, the Mesozoic's long warmth gave way to a colder, more variable world. The rocks that remain from this era still glow with its memory. Chalk cliffs, built from countless shells of marine plankton, line coasts as white monuments to the Cretaceous seas. Black shales beneath them hold the signatures of oxygen-starved waters, the buried breath of ancient oceans. Fossil forests at high latitudes preserve the pattern of endless day and gentle dark, their rings tight and even from seasons that hardly changed. For nearly 200 million years, Earth lived in this greenhouse comfort, its air heavy with carbon, its seas wide and warm. It was not a perfect calm, but a long harmony: tectonics, atmosphere, and life playing together in deep time. When we look at its stones today, we are looking at the preserved rhythm of that song, a world that knew no ice, only the patient shimmer of heat and water. And in that warmth lies a quiet truth. The planet has known gentler climates than ours, and harsher ones too. What endures is not a single temperature or age, but the resilience of a system forever moving toward balance, guided by chemistry, pressure, and time. Amber light gathers low on an ancient horizon, a warm haze that glows where ocean meets air. About 56 million years ago, the Earth stirred from its steady calm into sudden fever. The event is known as the Paleocene-Eocene Thermal Maximum, or PETM, a time when carbon, long stored in rocks and sediments, rushed back into the sky. The signal appears clearly in the rocks, a sharp, negative shift in carbon isotopes, a fingerprint of light carbon released in immense volume. Within a few thousand years, a blink in geologic time, the atmosphere and oceans were transformed. The source of the surge was complex, perhaps layered like the planet's own history. Volcanic activity along the North Atlantic seafloor intruded into ancient organic deposits, cooking them and freeing vast stores of methane and carbon dioxide. At the same time, the warmth that had already been building may have thawed methane-bearing clathrates frozen beneath seabeds and polar soils. Each pulse added to the next, until the air thickened with greenhouse gases and the oceans began to absorb the excess. What followed was global warming on a scale and speed almost without precedent. Temperatures rose by 5 to 8 degrees Celsius in only a few millennia. The poles, once cool refuges, became almost subtropical. In the Arctic, broadleaf forests spread where snow and ice would one day return. Fossil leaves showed dense canopies of palms and oaks, while crocodilian relatives drifted through northern rivers under the midnight Sunday. At high latitudes, the world glowed with a warmth that defied its coordinates. The tropics, already hot, turned near stifling humid, restless, alive with insects and early mammals adapting to strange new heat. In the oceans, change ran deep. The waters took in the carbon as they always do, dissolving it into carbonic acid. Surface layers grew more acidic, eroding the shells of plankton and slowly eating at carbonate sediments on the seafloor. Core samples pulled from ancient mud tell the story in color. Dark clays mark where calcium carbonate vanished, dissolved into water that could no longer hold it. Marine life survived, but not unchanged. Species migrated, evolved, or declined, each tracing its own curve through this thermal wave. Foraminifera, tiny shell-building creatures, recorded the chemistry of their time, their isotopes preserving the rhythm of the rise and fall. On land, mammals felt the warmth in their bones. Fossils reveal that several lineages, from horses to primates, shrank in size during the peak of the PETM. The reasons are still debated, but likely tied to heat stress and changes in food quality as plants responded to elevated carbon dioxide. Smaller bodies shed heat more efficiently, and in this hothouse world, that trait meant survival. Forests spread across continents, but their composition shifted dense. Evergreen canopies gave way to more open, drought-tolerant forms. Rainfall patterns altered, with storms swelling in some regions and drying in others. It was a world reshaped, not by ice or impact, but by chemistry itself. The atmosphere's carbon concentration may have doubled or tripled from pre-event levels, reaching more than 1,000 parts per million. The Earth's response followed familiar physics. Greenhouse gases trapped heat, feedbacks amplified the warmth, and ice vanished where it had lingered. Even the deep ocean warmed, disrupting circulation patterns that carried nutrients and oxygen. Life adapted as best it could, some thriving in new niches, others fading from the record. The PETM did not bring extinction on the scale of the great die-offs, but it rearranged ecosystems, redrew coastlines, and set the template for how climate responds to sudden carbon release. Recovery came slowly, over about 200,000 years. Weathering of silicate rocks, the planet's quiet and patient thermostat, accelerated under higher temperatures and heavier rainfall. Rivers carried dissolved minerals to the oceans, where carbon was locked away again in carbonate sediments. Plants and plankton buried more carbon in their tissues, drawing the atmosphere back toward balance. Layer by layer, the fever broke. The isotope curve in sediments bends upward again, tracing the long return to cooler conditions. The planet, resilient yet marked, resumed its slower geological pace. But the PETM left echoes. Smaller thermal pulses known as hyperthermals followed in its wake, each less intense but built from the same mechanism. Carbon inputs, warming, acidification, recovery. The pattern repeated, proof that Earth's system is sensitive to such disturbances, its balance precise but reactive. These events remind scientists that the carbon cycle and climate are bound together, two halves of the same breathing organism. Add carbon quickly, and the world heats swiftly. Remove it slowly, and the temperature drifts back down. The time lag between cause and cure stretches across millennia, but the link is absolute. Eventually, tectonic motion shifted the balance again. As continents drifted, new mountain ranges rose, and chemical weathering strengthened. Ocean gateways changed, the Arctic opened, the Tethys Sea narrowed, altering currents and cooling the poles. The planet moved toward the long decline that would culminate in Antarctic glaciation tens of millions of years later. The warmth of the Eocene gave way, inch by inch, to the chill of the Oligocene, then the rhythms of ice and thaw that would define later epochs. The PETM, though dramatic, became another note in the planet's vast repeating song. What makes it remarkable is its clarity. In oceanic cores, the layer marking the event stands out like a heartbeat, caught in stone, thin, distinct, global. Geologists trace it across continents and seas, a marker line that synchronizes the planet's scattered records. In those few centimeters of clay and silt lies a complete story, the cause, the consequence, the pros, to recovery. A blueprint for how the Earth behaves under rapid forcing. And perhaps that is why the PETM still speaks to us. It was an age when the Earth warmed fast, oceans turned acidic, and ecosystems shifted in response, all under carbon pulses smaller than those we release now. Its message is not alarm but reflection. The planet's memory runs deep, its reactions governed by law, not whim. The same physics that warmed that ancient world still guides ours. As the amber haze of that long-ago dawn clears in imagination, we see not catastrophe, but continuity. The planet breathes in carbon, breathes it out again, each cycle written in stone and shell. The warmth fades, the balance returns, and the Earth turns onward to patient, watchful, unchanged in its deeper truth. A single albatross moves across a grey horizon, its wings carving slow arcs above the Southern Ocean. The air carries a chill that speaks of deep time, of the moment when Earth herself began to change her breath. Around 34 million years ago, the warmth that had wrapped the planet since the age of the dinosaurs began to unravel. The Eocene gave way to the Oligocene, and the first permanent ice sheets spread across the high plateau of Antarctica. It was the turning point, the quiet doorway from a greenhouse Earth to an icehouse world. Before this change, the poles were mild, and forests climbed their slopes. Crocodiles swam near what is now Alaska, and palm trees brushed the winds of the Arctic. The oceans were warm from surface to depth, carrying vast currents of carbon and heat. But tectonic plates kept moving, slow and certain as tides. In the southern hemisphere, two openings formed, one between Australia and Antarctica, called the Tasmanian Gateway, and another between South America and Antarctica, known as the Drake Passage. As these channels widened, a new current was born, the Antarctic Circumpolar Current. It looped endlessly around the frozen continent, sealing it off from warmer northern waters. The Southern Ocean became a thermal moat, guarding Antarctica in isolation and feeding the spread of ice. At the same time, carbon dioxide levels in the atmosphere began to decline. Evidence for this shift comes from quiet clues, boron isotopes preserved in ancient shells, and the tiny openings on fossilized leaves that reveal how much carbon plants once inhaled. Together, they tell of a slow drawdown of greenhouse gases. Volcanic emissions decreased, while silicate weathering and organic burial captured carbon in rock and sediment. As the air thinned of its greenhouse blanket, temperatures dropped, and snow that once melted in summer began to last through the year. Ice accumulated, compacting under its own weight, until it became a continent-sized shield of white. The change rippled outward. Sea levels fell by more than 50 meters as water locked itself in ice. Shallow seas retreated, exposing continental shelves and reshaping coastlines. Climate zones migrated toward the equator, tropical belts narrowing, deserts spreading, temperate forests marching southward. Species followed these shifts as best they could, some adapting, others vanishing. The air itself began to feel different, its circulation sharpened by contrast between warm and cold. Winds strengthened, ocean currents reorganized. Earth had entered a new rhythm, one dominated by feedback loops of ice, albedo, and reflection. The cooling did not remain confined to the south. Over millions of years, tectonics continued their slow artistry. The Himalaya and the Tibetan Plateau rose high into the sky, born from the collision of India and Asia. Their peaks became engines of weathering, drawing carbon dioxide from the air through the chemistry of rain and rock. Rivers carried the dissolved carbon to the sea, where it settled into limestone beds. Each storm, each trickle of meltwater, contributed to the planet's gradual loss of heat-retaining gases. Mountains, in their silence, became architects of climate. Far away, the connection between oceans shifted again. The closure of the Central American Seaway, the narrow channel once linking the Pacific and Atlantic, transformed ocean circulation. As the land bridge between North and South America rose, it strengthened the Gulf Stream, sending warm currents northward across the Atlantic. That warmth, paradoxically, helped feed snowfall in high northern latitudes. Moisture carried by the Gulf Stream fell as snow on cold ground, adding mass to the ice sheets that would one day crown Canada and Scandinavia. The pattern of air and water, once gentle, now pulsed with greater extremes, wet and dry, warm and cold, building the stage for glacial drama yet to come. Through the Miocene, around 20 million years ago, the world's greenery changed its character. Forests gave way to grasslands across broad plains, shaped by lower carbon dioxide and stronger seasonality. Grazing animals evolved to meet the open light, and wind-blown dust recorded the expansion of dry regions. Climate oscillated, sometimes milder, sometimes harsher, yet always trending toward cool. Each swing was guided by slow celestial rhythms, Milankovitch cycles that tuned Earth's orbit like a metronome. Eccentricity, the stretch of the orbit; obliquity, the tilt of the axis; and precession, the wobble of the planet's spin, all work together to modulate sunlight at key latitudes. These rhythms determined whether ice would grow or melt, whether oceans would release or absorb carbon. As the ice expanded, its own presence amplified the cooling. Bright surfaces reflected sunlight back into space, increasing the planet's albedo. Lower sea levels exposed more land for weathering, which further drew down carbon dioxide. Oceans, too, adjusted. Circulation patterns shifted, and biological pumps carried carbon into the deep, storing it away for thousands of years. Glacial intervals became carbon traps, locking greenhouse gases into sediments while the world above shivered in the long cold. Then, as orbits shifted again, warmth would return, releasing the stored carbon, raising sea levels, and renewing the cycle. The rhythm was not constant, but it was predictable, the breathing pattern of an icehouse Earth. In this long arc from warmth to cold, nothing happened by accident. Each element, gateways, mountains, gases, and orbit, played its part in a chain of cause and effect. Tectonics rearranged continents, continents steered currents, currents shaped climate, and climate fed back upon the carbon cycle that governs temperature. The planet, though blind to intention, behaved with balance. Over tens of millions of years, it cooled itself from a greenhouse warmth to an icehouse calm, layering feedback upon feedback until ice became a permanent fixture at the poles. To imagine, it is to feel the patience of deep time itself, oceans shifting like slow breath, mountains rising grain by grain, air changing its chemistry so gently that no single moment marked the transformation. And yet, by the time the albatross lifted its wings over the modern Antarctic seas, the change was complete. The white continent stood alone, wrapped in its flowing current, the anchor of the planet's new equilibrium. It is here, at the meeting point of air and ice, that Earth still carries the memory of that ancient pivot, a memory written not in words, but in cold and salt, in snow that falls and never fully melts. A hush of frost drapes the world, as if the planet itself were pausing to breathe. Through that long quiet, snowflakes gather and dissolve, their rhythm echoing the slow heart of time. For the past 2.5 million years, Earth has turned through a pattern of ice and thaw, the great quaternary cycles. Ice sheets have come and gone in patient procession, sculpting mountains, redirecting rivers, and writing a story of rhythm in stone. The pattern has never been random. It follows the tilt and lean of the planet's axis, the shape of its orbit, the faint but powerful pulse of sunlight falling across the hemispheres. Each variation is small, yet over thousands of years, they become the metronome of climate itself. At first, the beat was quick by geologic standards. Early quaternary ice ages waxed and waned on cycles of about 41,000 years, guided mostly by Earth's axial tilt, the angle that sets the contrast between summer and winter. When that tilt grew steeper, summers became warmer, ice melted, and the planet breathed outward into interglacial warmth. When it shallowed, summers cooled, and ice returned, spreading from high latitudes to claim the continents once more. These changes were slow enough to escape any single lifetime, yet steady enough to leave marks that can still be traced. The U-shaped valleys in mountain ranges, the ridges of moraines that once marked the edge of retreating glaciers, the deep layers of silt that settled in calm meltwater lakes. Then, roughly 900,000 years ago, something in the rhythm changed. The cycles lengthened, stretching from 41,000 to nearly 100,000 years. Scientists call it the mid-Pleistocene transition. The cause was not one thing but many. A gradual deepening of ice sheet roots, the removal of loose sediments beneath them, feedbacks between erosion, temperature, and albedo. Ice had learned persistence. Sheets that once melted away completely now grew so thick and stable that it took tens of millennia to undo them. The planet's heartbeat slowed, and the glacial dance began to follow a longer, heavier rhythm, one that still governs our age. During those glacial peaks, the face of Earth was utterly transformed. At the height of each ice age, sea levels fell by more than 100 meters. Whole continental shelves lay bare, exposing new land bridges and corridors between once isolated worlds. The British Isles joined Europe. Siberia and Alaska met in a frozen plain called Beringia. Winds carried fine dust across thousands of kilometers, building loess deposits that would later nourish grasslands. The oceans, colder and more stratified, absorbed vast amounts of carbon dioxide, lowering atmospheric concentrations and amplifying the chill. Forests retreated toward the equator. Deserts widened. Tundra spread south. Life did not vanish. It followed the ice, adjusting in waves of migration that mirrored the planet's breath. Each glaciation's retreat was as dramatic as its arrival. When the cycles turned warm again, the ice melted in surges, and sea levels rose, sometimes by tens of meters within a few thousand years. Valleys once carved by glaciers filled with rivers and lakes. The Atlantic reclaimed its continental shelves. Vegetation belts shifted northward, recolonizing the tundra with forest and meadow. In these interglacial intervals, greenhouse gases rebounded carbon dioxide and methane, rising in step with temperature, not as cause but as amplifier. The cycle was always a choreography of elements. Orbit sets the timing, ice sets the brightness, oceans set the memory, and carbon follows the dance. Inside the polar ice itself, these stories are preserved like ancient lullabies. Cores drawn from Greenland and Antarctica reveal the pattern of temperature, trapped gases, and dust back through hundreds of millennia. Each layer is a season, a frozen diary of snowfall and sunlight. Ratios of oxygen isotopes trace the warmth of the air when each snowflake fell. Bubbles capture the breath of ancient skies, proof that greenhouse gases ebb and flow with the turning of ice. In marine sediments, foraminifera, tiny shelled creatures record the chemistry of the ocean as they lived and died. Their remains align with the ice record like harmony lines in a song, confirming that the Earth's systems move together, no section of the orchestra playing alone. Even within these grand rhythms, the planet's climate could change in an instant. Abrupt events punctuated the otherwise smooth waves of cold and warmth. Around 12,000 years ago, as the last ice age was ending, one of these shocks struck the Younger Dryas. A great pulse of fresh water from retreating North American ice flooded into the North Atlantic, disturbing the deep currents that carried heat northward. The consequence was a sudden return to cold, felt most sharply around the Atlantic basin. Glaciers advanced again, tundra replaced forest, and temperatures in parts of Europe fell by as much as 5 degrees within a century. Yet the event ended as swiftly as it began, the currents recovering, the warmth returning. Through all of it, life adapted. Mammoths and reindeer grazed along frozen steppes. Saber-toothed cats prowled the open plains. Humans learned to read the ice's rhythm for survival. The shifting coastlines and changing climates shaped migrations, languages, and myth. The narrow Bering Land Bridge allowed the first humans to reach the Americas. Later, melting seas cut them off again, isolating populations for thousands of years. In Europe, the retreat of glaciers opened fertile valleys where new cultures grew. The end of each glaciation was both an ending and a beginning, a thaw not only of ice but of possibility. The physics that governed these ages never faltered. Orbital variations, the Milankovitch cycles, set the framework. The tilt, the wobble, and the stretch of Earth's orbit dictated how sunlight was distributed. Ice and ocean responded, magnifying small changes through albedo and carbon feedbacks. When the planet cooled, oceans inhaled carbon dioxide. When it warmed, they exhaled it again. Clouds, vegetation, and currents followed in kind. No single factor ever led the dance alone. The climate was an ensemble, every part in conversation with the others, moving according to the simple logic of energy balance and time. We live now at the tail of this long cycle, in a moment of warmth between glacial breaths. The last major ice sheets reached their maximum about 20,000 years ago, then began their retreat into the present interglacial, the Holocene. The seas have risen, forests have marched north, and the climate, for a rare stretch, has been steady enough for human civilization to take root. Yet even in that steadiness, the memory of the cycles endures. It sleeps in the chemistry of the air, in the layers of ice beneath our feet, and in the continents still rebounding from the weight of vanished glaciers. The Quaternary is a lesson in patience. It shows that the Earth is neither fragile nor unchanging, but a system of balances slow to move, slower to forget. Each pulse of ice and warmth, each carving of valley and rise of sea, has written its note in the long symphony of climate. The melody continues still, quiet beneath our noise, reminding us that even cold has rhythm, and even ice can sing. 11,500 years ago, the last of the Great Ice Age loosened its grip, and the Holocene began a rare stretch of calm in Earth's restless story. Glaciers that had once groaned across continents melted back toward the poles, and sea levels rose, first quickly, then with a long, steady patience. The world that emerged was softer, greener, and kinder to the fragile experiment called civilization. Fields replaced tundra, forests grew where ice had once ruled. Rivers, freed from frozen banks, carried soil and promised through valleys that had waited in silence for the thaw. In this new warmth, the Earth found a rhythm it had not known for 100,000 years. Temperatures evened, the great seasonal swings relaxed, and the planet's energy balanced like a pendulum that had finally come to rest. Across the globe, early humans noticed the difference, not with instruments, but with survival. They settled, planted, and stayed. The air's composition, carbon dioxide around 280 parts per million, methane close to 700 parts per billion, offered conditions that nurtured grain and grass alike. The Holocene, though brief in geological terms, became the cradle of everything written, built, or remembered. Still, the calm was not perfect stillness. The climate pulsed within its own gentle bounds, guided by the slow clock of orbital mechanics. Earth's axis shifted, its orbit stretched and relaxed, altering how sunlight fell across the hemispheres. Early in the Holocene, summers in the north were slightly warmer, winters milder. By mid-Holocene, perhaps 6,000 years ago, temperatures across many regions reached a quiet peak, the so-called Holocene Thermal Maximum. Forests spread deep into what is now tundra. Monsoon rains reached farther north. Mammoths had vanished, but elephants and hippos still roamed along shrinking wetlands in Africa. Coral reefs thrived in oceans warmer than today's, and glaciers retreated to the highest peaks. The balance was delicate but self-sustaining, a long exhale after the Ice Age's sharp breath. Then, slowly, the pendulum began to drift backward. The same orbital cycles that once favored warmth began reducing northern sunlight each summer. Cooling crept in, so gradual it could not be felt within a lifetime. Snow lingered longer at high latitudes. Forests withdrew from the far north, yet even this return toward coolness remained mild, buffered by the ocean's stored heat and the steady exchange of carbon between air and life. Compared to the wild swings of earlier epochs, the Holocene's climate was a song in one key, its variations subtle, its harmonies consistent. There were interruptions, small reminders that stability is never absolute. Bow. About 8,200 years ago, a sudden chill rippled through the climate. A massive burst of meltwater from retreating ice sheets flooded into the North Atlantic, disrupting the ocean conveyor that carried warmth northward. For more than a century, temperatures dipped, rainfall shifted, and growing seasons shrank. Lakes in Europe froze where they had not for generations. Yet the planet recovered. As it always had, currents rebalanced, heat returned, and the great cycle continued. Later, during the mid to late Holocene, droughts would shape civilizations in subtle but decisive ways. the fall of Akkad, the drying of the Sahara, the retreat of Mayan cities beneath encroaching forest. Local catastrophes, yes, but within a global calm that persisted like a steady tide beneath waves. Across this interglacial age, ice sheets continued their long retreat. By 6,000 years ago, the Laurentide ice sheet once sprawled across Canada had vanished, leaving behind the Great Lakes. In Antarctica and Greenland, smaller remnants endured, their mass slowly adjusting to the planet's new warmth. Sea levels stabilized roughly 120 meters higher than during the glacial maximum, drawing the new coastlines we now recognize. Islands, once mountaintops, emerged across tropical seas. Shorelines became homes, and coasts became the edges of civilization. The Holocene's atmosphere, too, stayed remarkably steady. Greenhouse gas concentrations wavered within narrow limits, buffered by forests and oceans. Volcanic eruptions and solar variations brought brief interruptions, years of dimmed sunlight, slight coolings, but the climate never slipped into chaos. It was within this predictable calm that agriculture rooted itself. Wheat and barley rose from the Fertile Crescent. Rice spread across Asia's floodplains. The rhythm of planting and harvest depended on the rhythm of seasons that rarely betrayed expectation. Humans, at last, could plan beyond the day, beyond the year. From that predictability grew language, trade, and story. But beneath the quiet surface, slow changes accumulated again. The planet's geometry kept turning toward cooler summers in the north. Ice cores record the trend, a gentle slide toward another glaciation, one that might have begun in several thousand years had the system been left alone. Instead, something new appeared, an unexpected actor in the ancient play. In the past 2 centuries, humanity tapped the buried sunlight of ancient forests and released it to the air. Carbon dioxide, stable for millennia, began to climb past 300, 350, then 400 parts per million. Methane doubled. Nitrous oxide rose from fertile fields. The long plateau of the Holocene tilted upward, not from orbital rhythm, but from human hands. The response has been as physics predicts. The surface warms, ice melts, the oceans rise again. Water cycles quicken, wet regions grow wetter, dry ones drier. Heat pools in the seas, which absorb both energy and carbon, slowing change but ensuring its persistence. Ice sheets, slow to move but sure to answer, begin their retreat. Greenland's edge carves into the Atlantic. Antarctica murmurs under strain. The feedbacks are familiar. Albedo falls as ice gives way to water. Darker surfaces absorb more sunlight. The carbon cycle, obeying the same principles as always, amplifies what it receives. Still, within this shift, the Holocene's legacy remains. It taught the planet's dominant species what stability feels like, and therefore what it risks losing. Our calendars, our crops, our stories, all rest on that brief, benevolent pause between ice and heat. Even now, the same physical laws that shaped the ancient glaciations remain at work, impartial and exact. The Earth keeps its books in carbon and light, its memory inscribed in ice layers and shells. To stand within this interglacial is to stand in the eye of time's balance. Behind us lie frozen continents and roaring winds. Ahead, the unknown path of a warming world. Yet for now, the air still carries the softness of that long calm. Rivers flow in familiar channels. Seasons still turn with rhythm enough for breath, for thought, for harvest. The Holocene is both a gift and a lesson, the age that let humanity grow within climate's rare stillness. It reminds us that peace on a planetary scale is not the absence of change, but the gentle holding of it. The planet turns, energy moves, carbon trades its partners. And in the quiet between these motions, the world, our shared and temporary home, keeps its steady light. Starlight scatters like fine salt across a dark counter, then steadies and fades. The long arc of climate ages lies behind the eyes now, not as pageants but as sequences of causes. Fire cooled to steam. Methane and carbon dioxide maintained oceans beneath a faint Sunday. Oxygen rose and chilled the world. Then volcanoes restored warmth. Global ice sealed seas before carbon built and thawed the lid. Forests drew down greenhouse gases and invited a drawn-out ice age. Great eruptions pushed against the thermostat. Weathering pulled it back. Gateways opened and closed. Mountains rose. Currents rerouted. Ice advanced and withdrew to orbital time, carving coasts and shelves. An interglacial quieted the swing enough for fields to anchor. None of this asks for metaphor to be grand. Numbers and minerals carry the story well. The energy arriving at the top of the atmosphere, the fraction reflected by clouds and ice, the infrared retained by gases. Together they sum to temperature. Oceans buffer, rocks react. Life participates by storing, releasing, and transforming carbon and nutrients. Feedbacks grant stability until thresholds are crossed. Then new equilibria appear and hold. 7 ages offer a rhythm for sleep because they are orderly. Each links to mechanisms with names and tests, recorded in cores, outcrops and crystals. If wakefulness lingers, follow one detail to its rest. A shell locking carbonate, a root prying feldspar to clay, a stream carrying ions to the sea. If drowsiness wins, let it. The planet keeps its own ledger whether eyes are open or closed. Drift with that steadiness. The room is quiet. Breath falls into pace with waves you cannot hear. The world has been many things and remains one world, lawful across time. When sleep arrives, it finds you inside that calm.